Bus duct accessories. Moisture condensation. Introduction. Moisture condensation can occur inside a metal enclosed air-insulated busbar system whenever the temperature dips below the dew point. Condensation occurs when warm, moist, still air comes in contact with a cold surface. The cold surface chills the air to below the dew point, resulting in moisture condensation. When a metal enclosed air-insulated bus has been de-energized during routine maintenance or shut down, condensation can occur due to the variation in the atmospheric temperature. Such a situation can arise even when the metal enclosed air-insulated bus are lightly loaded. When condensation occurs, moisture along with the dust particles will settle on the surface of the insulator and provide a path of low impedance for leakage current to flow and result in tracking. The dielectric properties of some insulators can deteriorate with the absorption of moisture. As long as the temperature of the air inside the enclosure is maintained above the dew point, there cannot be any condensation. This will happen when the metal enclosed bus is loaded to a significant ratio of its rated capacity. It has been found that raising the internal temperature by 10 degrees Celsius alleviates the problem. When a metal enclosed air-insulated bus has remained in de-energized condition for a sufficiently long time, to hasten the commissioning process, it may be advisable to use portable hot air blowing equipment to remove the moisture and dust before the heaters are switched on. It is, therefore, the normal practice to install anti-condensation heaters inside the enclosure to elevate the temperature of the air above the dew point. The most effective solution combines heaters with control devices like hygrostats, thermostats, or hygrotherms. Thermostats trigger heaters when the temperature falls below a set point. Hygrostats turn the heaters on when humidity rises above a given threshold. Hygrotherms do both. Using hygrostats to control heaters is considered more energy efficient but more expensive. Thermostats seem to be the most popular way of controlling the anti-condensation heaters. Thermostats can be installed with either a fixed setting or with variable settings. Knowing the site conditions for a project, it is preferable to have a fixed setting for a thermostat. The use of an adjustable thermostat is an invitation for the user to reduce the thermostat setting to save energy, in the process, significantly increasing the likelihood of condensation. The quantity and the rating of the individual heaters will depend upon the volume of air inside the bus duct. A thermostat or humidistat can be strategically located to control an individual or a set of heaters. For example, 2 thermostats may be located one each at indoors and outdoors and connected to the respective cluster of heaters. The thermostat should not be located close to the heater element. The sizing of the heater element and setting of the controlling device, such as the thermostat, humidistat, or hygrostat, will depend upon variations in the ambient conditions and trapped volume of air inside the metal enclosed bus. The quantity and the rating of the individual heaters will depend upon the volume of air inside the metal enclosed bus. Anti-condensation heaters are located at regular intervals of approximately 3 meters or 1 per the standard length of a metal enclosed bus. It is a good engineering practice to have a separate heater pod assembly located at the bottom of the bus duct, in the center. The heater shall have a perforated safety cover. It is prudent to specify the maximum temperature rise of the cover. This temperature rise must be tested in a simulated bus duct section. The manufacturer of the heater must also guarantee the total life, in hours, when operating under rated conditions. Heater covers and fins are susceptible to corrosion since they operate under elevated temperatures. The material of the outer casing may be specified for the specific project. To maintain the desired temperature of the air inside the enclosure, heater pods are provided at strategic locations along the route. Heaters are also accommodated as close to the insulators and bushings as possible. Filters, breathers with silica gel. Breathers cum filters are installed on top of the bus enclosure. It enables it to expel or inhale air due to the variation of the temperature inside the enclosure. Sometimes, a container with dry silica gel is attached to prevent the ingress of moisture into the enclosure. Silica gel needs to be monitored for absorbed moisture content. Breathe drain with collection bottle. Drain cum filters are installed on the enclosure of the air-insulated busbar system at the lowest location to drain out the condensed water. The selection of the assembly is critical as it should be ensured that the degree of protection of the enclosed busbar system is not compromised with its installation. Breather drains are available which, when fixed at the bottom, perform both the functions. Breather drains that can breathe 0.2 cubic feet of air per minute at atmospheric pressure and discharge 50 cubic centimeters of water per minute are available in the market. Breather drains are manufactured up to a degree of protection of IP68. Thank you. For a comprehensive understanding of the theory and practices of busbar systems, it is advisable to read the book An Introduction to Busbar Systems, where contents are organized in a sequence for ease of reading and facilitates cross-reference. Please procure a copy of the book with a requisition to bala@busbarsystems.net.